Okay, there we go. We're recording now. All right, so as I said before, we're doing very similar to what we did last time for building up the matrix. So we have this thing right here, which by now people should be familiar with kind of what I'm doing here. So who remembers what I'm doing? Who remembers what I'm doing at this point right here, where I have this base table equals and then something? Yep, I'm initializing an empty dictionary. And who remembers what the next thing I'm probably going to do is? So I'm not going to iterate. Yeah, I'm not going to iterate over the dictionary because it's empty, but I am going to iterate over something and then add values to the dictionary based on it. So obviously I don't iterate over an empty dictionary because there's nothing in there. Typically I'm iterating over something else that's iterable and then using that to add values to the dictionary. So what we have here is, I'm checking the line length again just to make sure the line is not too short. I'm also checking the read ID, and that's kind of it's kind of a property of sequencing reads, but each read has a unique ID. The only issue is that the read IDs will not be unique if you have paired end data. And since I have paired end data, what you see me doing here is I'm putting the value into the dictionary under .1. And if I already have a value in the dictionary for the .1, then I'm putting it in as .2. So here I'm checking for a .1. If I have a .1, I'm putting it in as read ID .2. Otherwise, I put it in as .1. And then I have this long, nasty looking piece of code here, which we can actually take apart. So all we have to do is work from the inside out. So we see here that I have brackets, which means I'm either putting in an index, or since I have a colon, it means I'm probably putting in a slice. And we see that I'm doing something starting at analysis position start. So, okay, that kind of makes sense. And then I'm going analysis length plus analysis position start. So I'm really just taking a slice starting at some position of the length that I want to analyze. So clearly I'm taking a slice. And what am I taking a slice of? If I go out a level, I see that I'm taking a slice of line.sequence.sequence. So I'm just taking a slice of the DNA sequence. And in general, it's going to start at 0 and go out to 50, or index 49, the 50th value. So I'm iterating over, and under the read ID, either .1 or .2, I'm just putting in the first 50 bases of each read. I also have a check here on data limit, which just gives me the option to end this quickly. So I can end it after 10 if I just want to do some testing. If I don't have a data limit, then it'll just skip over this part and I don't break. And so with data frames in Python, you don't build them from lists of lists or just plain lists. You actually build data frames in Python typically from dictionaries. So I'm going to have it just run this and then print the base data frame. And right now I'm going to have it quit because I don't need it to do anything else. I just want to see the base data frame. And I have a little piece of test code down here, which is just going to actually perform the test. So people can mess around with that a little bit if they want. But what I see when I run it is if I look down if I look across here, I can see the column names, and the column names are read identifiers, which is almost what I want, except I really want the rows to be the reads and the columns to be the individual bases. So the columns go 0 all the way down to 49, which makes sense because I'm taking only 50 bases. So really I have just about the thing that I want here. So of course I don't immediately know how to transpose a data frame in Pandas, but occasionally you don't even have to click on the results in Google. So for example, transpose Pandas data frame, you immediately see that in Pandas, in the data frame functionality or in the data frame object, there's a method called transpose, which probably gets you where you want to go. So going back to this, I can print my data frame, but then I'm going to transpose the data frame and check it. And I'm going to check a few other things, like make sure that I'm getting my column names back at for base data frame 0. And now what I'm seeing is I have 50 columns of bases, and each row is a different read. So 50 bases from each read, that is what I wanted. I'm also seeing that the shape is about what I expected. It's 500,000 rows times 50 columns. Oh, value counts, yeah. The other thing I looked up is, so previously I mentioned looking up how to do, I previously mentioned how to count the number of instances of different values in a data frame. So this base data frame 0 is going to just go in the first column and count the values. So again, it's going down this first column and just counting up how many times I see each value. And what I saw in the first column is a certain number of T's, A's, C's, and G's, and they look relatively close, especially T and A. So I see a fairly similar amount of AT and GC, which is what I should be seeing. I also see a couple of N's, so those are bases that have no identifier. And I'm trying to figure out what structure is behind TODH because that looks like a really familiar protein structure.
No, just a geometric drawing.
Oh, okay. All right, so what I have now is a pretty good test of the data structure. So typically once I get a data structure I like, I'm going to get rid of all kind of the test code I have in here. So there's a whole bunch of stuff in here that's just printing and ultimately quitting in this function. But really all I need this function to do is return that base data frame that I like. So again, keep your functions very narrowly scoped so that they're easier to fix when something goes wrong. And in the case of this function, get base data frame should do nothing but take in a SAM file and whatever other pertinent information it needs and return a Pandas base data frame. So this is all test code, and I'm going to just get rid of all of it. And the only thing it really needs to do is return this base data frame down here. And then I'm going to have another function whose purpose is actually going through a base data frame and extracting out the counts at each position. So again, for this one, I'm going to import pandas. And here I have indices equals, and I'm just getting the different columns. So it'll go through and figure out how many columns there are and just get the indices for them. I'm initializing an empty dictionary just like before. And now I'm going to iterate over my list of indices. And in this case, I'm printing index just to kind of get an idea of what it's doing and also to monitor as it goes. But here it says base count table of index, and the index is going to be whichever index I have up here. And conveniently enough, my indices happen to be my positions. So it's going to build up a dictionary where the keys are positions, and then that's going to be equal to, and each one is going to be equal to the base data frame at the index, the value counts. So it's just going to build up a dictionary of value counts at each position. And then it's going to turn that dictionary into its own data frame. And in this case, it's going to print because, again, this is just test code. So I have it actually displaying what it's doing so that I can see if it's doing what I want it to do. And again, down here, I have test code to actually cause it to run. And that creates a data structure that looks something like this. So every row in this data frame is a different base. Every column is a different position. And at each cell, I have a frequency. So I have the frequency of N, and I have the frequency of A, T, G, and C. So again, I'm going to look through this, and I can get rid of all of the test code. So I can ditch some of the print statements. I can get rid of the quit, and I just need it to return its value. And in this case, I decided that probably a better structure might be something along these lines, where I just get a table of position and base count. So I can get that just by doing another transpose. So I'm going to return base count dataframe.transpose, and that pretty much handles that. And I get rid of all the prints and excess statements in there. All right, so this is where I start asking people's opinions. If I want to visualize the base frequencies of the first 50 bases in each read, what are some really good visualization options here? So feel free to put things in the chat if you have an idea for what a good visualization option is. Like, what kind of graph do you think would be ideal? All right, I have one guess of a histogram. So histogram is probably not necessarily the ideal. So keep in mind, I want to show people something, for example, percentage bar graphs, that's not a bad idea. It's going to get pretty dense. How about just a regular old line graph where the y-axis is the base count and the x-axis is the position? So it obviously depends how you would want to present the data. Typically for base frequencies across there, cumulative base count, that would be an interesting one too. So for this one, we're going to do a regular old line graph, in part because they're still one of the most useful plots out there to look at trends. And they're also one of the easiest things to generate in matplotlib. And I have somebody asking for smaller read lengths, line graphs would be okay, but for really long read lengths. So it turns out line graphs will still be okay for really long read lengths. Typically, if you're looking at base frequencies by position, a lot of times it should be pretty stable, and it should pretty much at every position reflect the GC content of your genome. And typically for these things, what you really want to notice are if you have any spikes or valleys. So in PyPlot, you can actually tell it how you want it to show different lines. We have different color options, and we have different sort of line or marker types. So for example, if I want a blue solid line, which is actually a pretty common choice, it would be B dash, and I'll show you how to add that. Okay, I have a question. Is PyPlot the same thing as matplotlib? PyPlot is an object within matplotlib, and it's essentially the canvas that your plots live on. So it's both your canvas, and it's kind of a smart canvas that can draw on itself. So you can tell PyPlot to draw just a regular line graph on itself or a histogram, and it'll do that. A stacked color bar plot would also be really cool. It might get a little bit complex, but that might be an interesting way of doing it as well. And a lot of it's going to depend also on your use case, because typically you make your visualizations with the idea that you want somebody to see something, or you want people to not be distracted by certain things. So we have a function here that'll generate the plot for the base counts. So we can hand it one of those base count data frames that we just created, and we also need to pass it a length. So we're going to import PyPlot as PLT, and we have our base marker. And I guess this is proof that I wasn't always in bioinformatics, is that I know that there are actually standard colors for each base, and this chart represents them all. So here's an interesting statement for base in ATGCN. And what's interesting is if you try and iterate over a string, it'll just give you back letter by letter. So I could have actually just handed this a list also with A, T, G, C, and N, but it's actually a lot faster to type it out as just a long string and iterate over it letter by letter rather than having to put in quotes and commas for each of these individually. And so for each of these, I'm telling pyplot to just plot out, and it's going to have, in this case, the first argument I give it is the X values. So in this case, I'm just giving it a range because it's going to go from 0 to 49. I'm going to give it the base count data frame of each base. I'm going to give it the base marker for that base. So again, it's going to go through A, T, G, C, and N. So it'll do the base count data frame for A first. It'll do the base marker for A, which is going to be a blue line. And then the label is going to equal base. And the label is useful because it'll use this when it's generating the legend. And what's cool about this is if for some reason I had another base, like let's say I was also looking at inosine or some other unusual base, I could just add inosine to this and everything else will be handled below, including the iterative plotting of inosine frequency at different bases. After that, it's just a couple of other simple lines. So I'm giving it an X label of position, a Y label of counts. I am telling it to display its legend. And then if I uncomment this, it'll pop the plot in a new window. Otherwise, it'll save the figure. And then I have a couple lines to actually cause us to run. And when you run it, you'll see something like this. So I'm actually going to give people, let's see, it's 2:06. So let's go until about 2:20. I'm going to give people a chance to run this and play around with it. Definitely a good opportunity to also look up how to do different kinds of plots. So the nice thing is you have basically a data set here and you have a good way of accessing it. And if you want to try making stacked bar plots or anything else, this is definitely a good chance to play around with that. So I'll hang around in case people have questions. And I have a question saying, why do I use a B dash versus B? So I think by default, it will do a B in a solid line. It's either going to do a B in a solid line or a bunch of dots for B. But B dash is specifying explicitly that I want a blue solid line. So Todd Yates is wondering why I have two different read line IDs. So when you do sequencing and you get back your SAM file or your BAM file, every read is going to have its own unique read ID. The exception to this rule of uniqueness is if you had paired end reads, both paired end 1 and paired end 2 are going to have identical read identifiers. There's just going to be other things in their data that says one is paired end 1 and one is paired end 2. So the way we're dealing with that is when we put everything into the dictionary, since we don't care about distinguishing paired end 1 from paired end 2, we just don't want them to overwrite one another. We're checking to see if we already have that read ID in there under read ID.1. And if we do have that read ID in there under read ID.1, we're going to put the next one in there under .2. And that'll keep our paired ends from overwriting one another. All right, I have questions from Mo Ishihara. So first question, what does data limit do? The purpose of data limit is if I'm just doing a test and I don't want to analyze everything, I can set a data limit and, for example, have it only analyze 50 lines. And I have a question on line 19. And I think you're right, actually, that would be a mistake. Okay, yeah, I think that's actually an error in this one. Because I was previously calling the variable quality. I remember at one point I was calling that variable quality list, and I changed the name to base table. So it should actually be length of base table, not quality list. I'll go back and fix that. Yeah, that's from Histogram Maker. All right, so one of the last things I want to go over today, hold on real quick. So there's a really neat Python library called PySam. And the way in Python you typically install packages is you do pip3. If you're using Python 3, it'll be pip. If you're using Python 2, nobody should really be using Python 2 anymore. That system is officially deprecated. So pip3 is how you install Python packages. And I'm just going to try to install PySam. Oh, whoops. pip3 install PySam. All right, and we see that we get an error here. And I'm just going to actually cut ahead and say that if you tried to figure out why this wasn't working, what you'd start figuring out really quickly is you pretty much can't install PySam on Windows machines. It has dependencies on Linux, and it just will not install on Windows machines unless there's a bunch of stuff you go through. So how do I get this to run on a Windows machine? I'm going to introduce something called Docker. So I'm telling it to run a Docker container called Ubuntu. I'm telling it to run /bin/bash, which is the command prompt from the container. The two other things are telling it I want an interactive terminal and I want it to delete the container when I'm done. So the question on line 19, can you compare length and Boolean? No, that'll cause an error. I believe by that point, I've checked to see if there is a data limit. So if there's no data limit, it should evaluate to false and drop out before that. And if there is a data limit, then it's presumed to be an integer, and it'll try and compare lengths. So say that not having that in front of me right now. All right, so what you saw it do here, it very quickly downloaded an image for an Ubuntu Docker. And I'm actually right now, even though I'm on my Windows computer and in a Windows command prompt, I'm actually in Ubuntu. So for example, commands that wouldn't normally work in Windows, like ls, show that I'm in a typical Linux file system. What's also cool about this is I can do typical Linux installation. So I can do apt update and just have it pull down all the latest Linux stuff. Which I realize it's doing slowly right now because I have audio and video stream going. All right, and then I can do apt actually, I'm going to skip out of this. All right, I'm just going to pull down a Python Docker instead that already has all the Python goodies pre-installed. And side note, it really is this easy to pull down what are essentially virtual machines onto your computer. So a Docker container isn't a true virtual machine. It's running on the same kernel. It's not walled off, but it gives you the ability on a Windows computer to do a lot of stuff that you would normally have to set up a Linux computer or Linux virtual machine to do. And as we see here, I have, oh, Python 3.8 is up now officially. Cool. So this one just came out a couple weeks ago. So on this one, if I do pip3, I have pip3 functionality already in. And this will let me install PySam, whereas Windows would basically be a strict no on it. And it's already installed PySam successfully. And with this Python package, I can read SAM and BAM files pretty trivially. It becomes very easy. All right, if you can hold on for 1 second, I have somebody who looks like they're trying to call me very urgently.
Hi, everybody. I'm going to take this time to take attendance. So everybody paying attention, please, in the chat area, put here if you're attending. And I hope the ones who are listening will do that. Especially the ones taking it for credit.
Hi, Eli. I have a quick question for you.
Yeah, who's
Is
this?
that okay? This is Sarah Makanani.
Oh, okay, what's up?
Yeah, I sent you an email, so I'm sorry to bother you, but I got a hold of Jean Gray, and she said that enrollment has been bumped and to please register before tomorrow, but I've been registered for this course, so I'm not really sure what she meant by that.
Oh, did he,
Sorry.
yeah, Gene, did he, so you're trying to drop, right?
No, I wanted to get credit for this course.
Okay, and let me look into the email because I'd rather just talk there, okay?
Okay, thank you.
Welcome. Give me 1 second. Aliyah, can you refer yourself to the chat room so I could talk to you about that?
All right, sorry about that. I'm back. I'm part of a group that's developing bioinformatic apps for coronavirus testing, and there was an urgent issue I had to address for them. So anyway, what we see here is that in Docker, I was able to do things in Windows that I could normally only do in Linux because it's actually running Linux as basically an application or as its own process. The other cool thing about Docker is Docker has what are called Docker files that define how basically this operating system as an application is put together. So if you've ever encountered issues of a program running on your computer but not somebody else's, or somebody else's program not running on your computer when it ran elsewhere, this is actually one of the best ways to deal with it. Because Docker files all have these predefined installation files, somebody running off of the same Docker file should be able to run all the same programs. And typically a Docker exists just to run one program. So this is a really good way to make sort of scientific computing and bioinformatics very reproducible between systems. So you're probably wondering what the best way to learn this is. Let me drag this over here. All right, so I'm going to introduce something called katacoda.com. So Katacoda is a really cool site. There's actually a lot of stuff you can learn here, but it gives you these nice little environments to get practice on. So the one we're going to check out today is Docker. And essentially, if you work through this one, you'll start getting you'll become basically a Docker expert. So it'll start off with these scenarios. And so for example, starting with this first scenario, it'll walk you through how to do these things. So for example, setting up a container just runs as a process. And we'll see here the command to actually run the container is this one. If you want to sort of cheat your way through, you can just click on there and it'll actually type in your command for you. Personally, I always like to actually type these out myself because it kind of gives me a good feel and a good way to remember how to do this. But getting some practice with Docker, I think in the next couple of years, we're going to see a big push towards Dockerizing scientific applications because it really gets rid of a lot of the difficulties with installation and it increases the reproducibility between people's environments. And if people have questions about this or other things, I'm more than happy to help. But I think at this point, yeah, it went quite a bit faster because usually in class, I'm usually running around helping a lot more people and going over a lot more code. I obviously can't do that here in Zoom, but I'll stick around for a little while if anybody has any questions. Otherwise, I'll see people around. Everybody's free to try and add me on LinkedIn. I'm pretty easy to find on there, and I'm more than happy to keep up with former students or anybody who wants to add me on there. If you have questions in the future, I'm more than happy to help.
Before everybody goes, anybody who didn't say here, please send here now before you leave because I need to take attendance on the chat room. Especially the ones taking for grade. So looks like I got a lot of people. So, all right, thank you.
I didn't. Hello.
Yes.
Hear me? I didn't say here yesterday, but I was here.
Well, I can't prove that now. So.
Okay.
Is that Khadija?
Yeah.
Okay, yeah, I saw you yesterday.
Okay, take your word for it.
Okay.
And Michael, can you send me the transcript for the chat so I can take down attendance? Because for some reason my desktop is acting very slow, and I wasn't able to jot down names. So
Yeah, sure. I think the transcript of the chat should be included with the course when I upload it.
okay, cool.
So I think I upload the chat transcript too.
Yeah, well, I guess when I see it later today, I'll just check it out. I'll send the quiz out to everybody else later today as well. It's just
Okay,
that
perfect.
my remote desktop is acting very slow, and it's like I can't get anything done.
Ah, okay. All right. Thank you very much.
All right, thank you.
So like I said, if anybody wants to reach out, if you need help developing a program, or you get some challenge in the future and you just want to know, you want some advice on how to approach it, I'm more than happy to help.